Don Mulchaey, yeah, it's his second visit to our club. He came in last February of 21. Last February of this year. That's right. Anyway, he gave such a stimulating talk. We decided early on, or at least I did, that we should have him back. So he's back today, and he's got a very impressive curriculum vitae. He's the director in Crawford H. Greenewalt Chair at the Observatories of the Carnegie Institution of Science, which is in Pasadena. It was founded in 1904. That's when my father was born. The observatories is world renowned for its research on the evolution of the universe. In addition, Dr. Mulchaey is a science deputy for the Carnegie Institution for Science, which is the observatory's parent in Washington, D.C. He's the 11th director of the observatory, and he took on that position in 2015. He also oversees Carnegie's campus in Pasadena, as well as the observatory's large telescopes facility in Los Campos, Chile. He's also on the board of the giant Magellan telescope, a next generation telescope being designed in Pasadena. He's a frequent consultant to NASA and the National Science Foundation, and he created the annual Carnegie Observatories Astronomy Lectures, which is a popular series held each spring at the Huntington Library. His topic for today, the search for life in the universe, which Steve Shearer talked a bit about in his comments earlier. This is a topic of no greater interest in today's astronomers and the public. So I could go on and on with his background and what he's done, but I think we want to hear from him. So I'd like to have Dr. Mulchaey come in and take over here, Doctor. Thank you very much for coming again. I know he wanted to come to a live meeting, and we wanted him for a live meeting, but that just couldn't happen yet. So anyway, Dr. Mulchaey, please.
Wow, thank you very much for the introduction, John, and thank you for having me back. Let me start by sharing my screen here, make sure everything's working. And you can see that, right?
Right.
Nice. Okay, we'll go. There we go. Perfect. Yeah, so thank you again for having me back. I was, in fact, hoping I would be able to do this in person. It's always much nicer to be able to give these talks in person, but it turned out to be okay because I'm actually in Washington, D.C. at the moment anyway, so it made my life a little easier to not have to fly back to Los Angeles so rapidly for my trip. So today I'm going to talk about really one of my, perhaps my favorite topic in astronomy, which is the search for life elsewhere in the universe. And this is, of course, I think the question I get asked most often by people is, you know, do I believe there's life elsewhere? And as we'll talk about here, I most certainly do. And this field has become a hot field because of the discovery of planets around other stars. Most of us grew up knowing about the planets in our solar system, which, you know, for many years, there were 9 planets known until Pluto got demoted about 15 years ago to a minor planet. But since that, over the last 2 decades or so, astronomers have developed techniques to study planets and find planets around other stars. And so we call these exoplanets. That just means a planet around a star other than the sun. And as of today, I looked up the number, it's almost every day we're finding more. We're almost up to 5,000 planets now known in the universe. And so this is really remarkable. And this, the fact that we're finding so many of these planets has really opened up the opportunity to search for life on them, as I'll talk about today. And this plot here, it's a little bit complicated, but maybe not so bad, but it just characterizes the various planets that we found, those 5,000 planets, by their properties. And so if you go along the x-axis there where it says orbital period, that's just how long it takes these planets to go around their star. And this, as you go up on the y-axis, they get bigger. So you can see on the right-hand side there, you'll see there's little Earth, Neptune, and Jupiter to kind of give you a scale. And so there's a lot of different exciting types of planets we're finding in the universe. But the ones we're most interested in are those that are called the rocky planets, because those are planets like the Earth or Venus or Mars, where they have a solid surface, because we think those are the best places for life. But I'll talk a little bit about that in a minute. But before I do that, I always like to step back and ask the question, should we expect life in the universe elsewhere? And if you ask experts, and I put experts in quotes here because there really are no experts in the sense that we only know of life in one place in the universe. But there are people who spend a lot of time thinking about this, myself included. And if you ask those people, there are some people who believe we're the only life form at the moment, at least in the Milky Way galaxy, to others who think that there could be hundreds of thousands of civilizations right here in our home galaxy. So I always like to start by doing a little math experiment. Who doesn't like to do math in the afternoon? To kind of give you an idea of the sense of scale of just how many planets there are in the universe. And so that's in fact the question I want to calculate. I'm going to walk you through a little quick calculation to go, how many planets do we think there are in the universe? And so the issue is here, although we've found close to 5,000 planets, our techniques only allow us to search in our nearby neighborhood, in the nearest few thousand stars around the sun. And that's a very tiny portion of the universe. In fact, it sounds like a lot, but it's really not. This diagram here shows you a diagram of what our Milky Way galaxy would look like. This is our home galaxy. And you'll see the sun is labeled and there's a little circle around it. And that shows you the area of the universe that we've been able to look for planets so far. It's a tiny fraction of our home galaxy. And so to really estimate how many planets there may be in the whole universe, we're going to have to extrapolate based on what we see in that little area. And based on what we see in that little area, it appears that an average of each star in the universe appears to have about 5 planets on average. So I'm going to assume that. I'm going to assume if every star in the universe has 5 planets, how many stars are there in the universe? And so to do that, we can add up stars because stars are bright and we can see them pretty far away. And it turns out that stars don't occur randomly in the universe, but they occur in these beautiful collections like you see here. This is a beautiful image of a galaxy. This is what our own Milky Way would look like if you could step back out and look at it. And what you're seeing here is the light from 200 billion stars. That's a lot of stars. So in the case of the Milky Way, the sun is one of those 200 billion stars. So if every galaxy has 200 billion stars, and if each of those stars has 5 planets, you can multiply those numbers together to estimate how many planets are in a typical galaxy like the Milky Way. And when you do that, you get to 1 trillion, a very big number. So that means we expect even in our own Milky Way galaxy, there are probably 1 trillion planets, of which Earth is just one of those trillion planets. It's a pretty big number. But you can ask the question, the Milky Way is one of many galaxies in the universe. How many galaxies are there in the universe? And to do this, we can actually count. And this is one of my favorite images. This is a deep image taken with the Hubble Space Telescope of the universe. Basically pointed the telescope at a very tiny region on the sky. It's hard to do this on Zoom, but I'll try. If you take your finger and just pinch it in projection up on the sky, that's what this image corresponds to. Just a very tiny little slice on the sky. And every single speck of light you see in this image is a galaxy. That is, each one of these, the tiniest little things you see on this image on your screen, is a system with hundreds of billions of stars and on average 1 trillion planets. There are 3,000 in this image. You don't have to count them. I've done that. Well, I haven't done it, but we know we've counted it. And those 3,000 occur, as I said, on the tiny pinch on the sky. This should give you a sense that the universe is just truly immense. So now if you take this average of 3,000 in this little pinch of the sky and average it over the whole sky, what you find is that there are approximately 10 trillion galaxies in the universe. So a huge number. And since each of these trillion galaxies has about 1 trillion planets, you can multiply those numbers together and you get this incredibly large number under total. That's a 1 with 25 zeros. Now, I don't even know what that number is. There is no name for that number. At this point, you get to things that are well beyond billions and trillions. I look at this huge number and say, how could we possibly be the only place in the universe with life? This number is just so incredibly large that you can imagine if you said maybe only 1% of the planets in the universe might have water, you could knock out 1 zero or something of that sort, or 2 zeros maybe. Anything you do is going to leave you with a huge number here. The opportunities for life are immense in the universe. And that's the whole point of this calculation. By the way, you see I put down there, I tried to find some number to relate to this. It's hard enough to relate most of us to 1 billion, or let alone 1 trillion, let alone this number. And so the closest thing I could come up with was grains of sand on Earth. And this number is 1 billion times the number of grains of sand on Earth. That is, the universe has 1 billion more planets, billion times the number of planets as grains of sand on Earth. You should feel very small at this point. The universe is immense, and the opportunities for life are great. So now that I've convinced you, hopefully, that we should be able to, there should be lots of opportunities for life, well, how are we going to go about finding it? So we're going to go back to look at these planets that we know of, because these are the best ones to study. And in fact, as I said before, we're going to really concentrate primarily on those rocky planets because we think those are the best opportunities for life. And there's really 3 different techniques astronomers are using to look for life in the universe. The first of these is the least likely, but in some sense the most exciting. And this is the one you may be thinking of. And this is actually looking for direct communication from aliens. This little image here on the left shows a series of radio telescopes pointed out into space with obviously an artist's rendition of a potential alien. And so there are organizations. SETI is the most famous. SETI stands for the Search for Extraterrestrial Intelligence. And this is an organization that uses radio telescopes to look out in the universe and look for radio signals from aliens. And why would we do this? Well, we do this because we know here on Earth, we are sending radio and TV waves out into space. Anytime we're transmitting radio and TV here on Earth, those waves that are used for us to hear the radio or to see TV have actually propagated out beyond the Earth, out into the solar system and out into the universe. And so in fact, we've been doing radio signals for over 100 years now. That means these radio waves, they travel the speed of light, which is very fast. And so they have been propagating out into the universe. And so we can ask the question, can we do the reverse experiment? Can we find those signals from aliens that have propagated back to Earth? I love this. One of the great things about the internet is you can find any sort of diagram. And this one is one of my favorites. Somebody who was thinking about this topic pointed out that I Love Lucy aired for the first time about 70 years ago. This means those signals from I Love Lucy have traveled out this very large distance, about 70 light years, out into space. So it's entirely possible that there are aliens out there watching I Love Lucy and finding us. And as I said, radio predates TV by a good 30, 40 years. So those radio waves, those first radio programs here on Earth have propagated out even further. So how does this work? Well, this is some nice little diagrams here on the left, which this is a plot of all the stars that are within that volume where our radio waves could have reached by this point in time. So this diagram, think of the sun and the Earth are kind of at the center of this. And these waves have been going out. Every dot you see on that diagram on the left represents a star that could potentially be listening or have heard radio or TV waves from us here on Earth. That's a good number of stars. It looks like it's a good number of stars. Now, if you look on the right-hand panel here, once again is a diagram, a picture of what the Milky Way would look like. And you'll see the tiny little region that this corresponds to. It's very, very small. So in fact, although there's a lot of stars that our signals could have gone out to, in fact, we barely made a blip in our own galaxy. So in fact, most alien species in our galaxy would not have heard from us yet because our waves haven't propagated out very far. Unfortunately, while this is an exciting idea to think that we could look for radio and TV waves or they might see us, there's a complication, and that complication is this weird law in physics, which is called the inverse square law. It's not very weird, but what it says is that the signals as they propagate outward, radio and TV waves and light waves, that they fall off in intensity very rapidly. They fall off by what's called the inverse square law, which means as something goes out by a factor, it drops by that factor to the second power. And so as a wave with a certain strength goes out by a radius of say 2, it will drop down by a factor of 2 to the second power, which is 4. So it's already a factor of 4 weaker. By the time it goes out to a radius 3 times as big, it's 3 to the second power, which is 9, 4 to the second power is 16. So very rapidly, those TV waves and radio waves that we're emitting have been diluted. And in fact, if you actually look at this in detail, you would see that unfortunately, the waves, even by the time they get out to the orbit of Pluto or in our own solar system, our waves would be much too weak to actually detect. They would just appear as noise to an alien. So unfortunately, I think this technique is unlikely to be very fruitful for us. That doesn't mean we couldn't ever communicate with an alien species. And in fact, there are ways for the signals to be stronger. One can imagine, for instance, sending a laser. So we have lasers, which are of course, a very focused beam of light. You could imagine an alien, for instance, beaming a laser light at us in a way for us to find. And that is possible. But given how immense the universe is and how many planets there are, there's 1 trillion in our own Milky Way galaxy, you'd have to be looking at the right place, the right time, at the right frequency and you'd have to be able to interpret it as coming from aliens. So the odds are, in fact, unlikely that we're going to communicate directly with aliens during our lifetime. That's unfortunately sad, but that's the reality. So astronomers have worked on other techniques to look for life. And these are more likely to, I think, lead to success, but they're also maybe not quite as exciting. But the first is to actually look for what we call biosignatures, that is evidence for life, by studying how the life has impacted the environment of the planet it lives on. And this is important because we know here on Earth that life has impacted our atmosphere. Our atmosphere was very, very different initially. Here's a little diagram which kind of gives you a quick little history of how the Earth's oceans and atmosphere on the left here came to be. The Earth formed without an atmosphere and without oceans. But over time, as volcanoes and other seismic activity happened, material from the center of the Earth would have been brought up and ejected. And this is, in fact, how our atmosphere formed. So we primarily, in the case of the Earth, we would have had carbon dioxide and water vapor in our atmosphere, all coming from volcanoes. And eventually the water, of course, would rain, and this is how the oceans came to be. And so our atmosphere on Earth initially was really just these elements. It was really just carbon dioxide and water. But we know that our atmosphere contains a lot of oxygen. This is molecular oxygen. This is with 2 oxygens. We rely on this oxygen. This is the oxygen that we breathe. We know the atmosphere has things like ozone, which is 3 oxygen atoms together in a molecule. All of these things have come from plant life. And so on the right, it's a little bit complicated, but this is a diagram that shows the history of the Earth you start at the origin where it says minus 4.5 there. That's when the Earth formed. And this line shows you the amount of oxygen in the Earth's atmosphere over time. And you'll see that there's been these huge increases in time, particularly over these are billions of years, the last billion years. This is because of that plant life. The fact that oxygen is the second most common element in our atmosphere is due entirely to the fact that we have life here on Earth. And so, because we don't believe oxygen can form in this format, at least in any other way, if one could see oxygen in an atmosphere of a distant planet, one could imply the existence of life. And similarly, an alien civilization might be studying Earth. They could study the composition of our atmosphere. That's much easier than doing other things. And based on that, they could determine that we were here. Now, this is a little bit complicated here, but this just shows you how astronomers do this. We do this with our telescopes by looking for these features. We can study the atmospheres directly of these planets. And basically, you don't have to worry about the details here, but you'll see all these big wiggles. These wiggles are due to these things, these elements in our atmosphere: oxygen, water, methane, which is another one that comes primarily from life here on Earth. And in fact, in detail, there are actually features in the atmosphere of the Earth that reflect the fact that we have like the Amazon and plant life over a big portion of the Earth. There's features that have to do with, in fact, the oceans. And so there's lots of different things one can tell from astronomy by being able to study the atmospheres of these planets. And so this is an experiment we're starting to do, and I think it's going to be quite interesting. It's a very difficult experiment. And for this reason, you really need big telescopes. And so one of the telescopes that we're building at Carnegie, which will be at our site in Chile, it's called the Giant Magellan Telescope. I think I talked about this last time, most likely. This is a telescope that has 7 big mirrors. Each mirror is about 25 feet across. So it's equivalent of one giant 80-foot mirror. It's a huge telescope. The dome is about 24 stories high, to give you an idea of the scale here. This telescope is really being designed to study those atmospheres and look for that oxygen. And I'm pretty confident within a decade or so, we're going to find evidence of other places in the nearby universe that have atmospheres very similar to Earth. And that's going to give us an indication of life elsewhere. The other method, though, the third and final method to look for life, is to ask the question, are we going too far? Maybe we should look in our nearby neighborhood, our own solar system. That is, the planets and the moons that orbit the sun. And so these are the 6 places that astronomers are most intrigued about to look for life in our own solar system. And one of them you'll know very well, which is Mars, of course. And we know one of the reasons we're sending all these rovers and things to Mars is to look for evidence of life. And Mars is interesting because Mars has temperatures that are not terribly extreme compared to Earth. It's colder than Earth, but sometimes it's actually pretty decent. We know Mars has water. In fact, you can see evidence of the water in these polar caps that you can see there in the North and South Pole. That's frozen ice, carbon dioxide and ice and water ice mixed together. And we know that early on, Mars probably had oceans or things similar to oceans and rivers and lakes. So at least at one point in its history, Mars was a good place for life. Most of the experts now think that perhaps that's not the case anymore. And so a lot of these future missions will be looking not only for present life, but for evidence of past life. Because Mars may have had life that started in some simple form, but because the conditions kind of got worse over time, it may not have propagated. But Mars is still very interesting. But these other 5 ones are ones that you may not be thinking of so much, particularly that top row there, those 3 right after Mars. These are really fascinating places. These are real images of these 3 moons, 2 of Jupiter, 1 of Saturn, that were taken by our colleagues at JPL here in Pasadena. And each of these, why are these moons of Jupiter and Saturn? They would seem to be not great places for life. Jupiter and Saturn are very far from the sun. We know they're pretty cold. How could you have life on these places? Well, the reason we think they're interesting is because we know in all 3 cases here that there are oceans in these 3 moons are covered in oceans. And on top of the ocean is a layer of ice because the outer part of the moon is very, very cold. But the inner parts are warm because they have tidal interactions with Jupiter and Saturn. And so these have liquid oceans that are covered, as I said, with a layer of ice. So how do we know that there's liquid underneath that ice? We can see it directly in these geysers. And these images here are really, really quite nice. The one on the right is an older image, so I'll concentrate on the one on the left, but they both show this. You see these things that look like kind of white spotlights coming out. Those are actually geysers of material that is popping through the ice out into space. And so we directly know from these geysers that there's liquid underneath this ice. And so there's a lot of hope that these liquid oceans could be places where very simple life forms could be forming. Because that for it to be liquid, the temperature has to be pretty temperate. So there's a lot of activity, a lot of interest in these moons. NASA is already talking about sending missions that will go and sample some of the geysers to try to see if there's any evidence of life in them. The last 2 things on here are also very interesting. Titan is another moon of Saturn. Titan, you don't see the surface of because it has such a thick atmosphere. Titan has an atmosphere thicker than Earth's atmosphere. And the reason why Titan is interesting is because it looks an awful lot like the Earth looked about 4 billion years ago when we know life formed. And we know Titan has some liquid on its surface because we've done radar experiments. So it has lakes, not oceans, but lakes. And between that and the thick atmosphere, we think it may be a place where once again, some primitive life form could be forming. And so NASA also has plans to go to Titan and land on the surface at some point and try to sample that. The last place on here is one that I say I've been pretty skeptical of, and this is Venus. And Venus is our nearest neighbor. Venus is almost the same size as Earth, and it has a very, very thick atmosphere. In fact, its atmosphere is so thick that Venus has what we call a runaway greenhouse effect. That is, it is just heated and heated and heated up. And so Venus is a very hostile place. It's actually extremely hot. On the surface, it's almost 900 degrees Fahrenheit on the surface. So how would you have life on a place that's 900 degrees Fahrenheit? Well, the reason it's interesting to us is because although the surface is very hot, the upper atmosphere of Venus stays a beautiful temperate 70 or 80 degrees most of the time. And so Carl Sagan, the very famous astronomer, suggested in the 70s that perhaps you have a life form that could live in Venus, kind of swirling around in those upper areas, never reaching the surface where it's hot, never going out into space, but just kind of staying in the upper atmosphere. So this is an intriguing idea, but I'd say most of us thought this is a pretty crazy idea, but why not? But then last year, in September of 2020, astronomers reported the detection of this very interesting element called phosphine. And the reason this element is interesting is because phosphine does not occur naturally by geology or anything like that. And on Earth, the only time we see phosphine is when there's bacteria around. It somehow has some association with bacteria. So the detection of phosphine in the atmosphere, upper atmosphere of Venus, certainly suggests that potentially there's bacteria living in the atmosphere of Venus. Maybe life is right next door to us all this time and we didn't know. So this just shows you what a phosphine is. It's just 3 hydrogen atoms and a phosphorus atom. But the amount that was seen on Venus is so large that it really suggests that there has to be a good amount of bacteria living in the atmosphere of Venus. Now, unfortunately, as often is the case, the first claim has not been has not been verified by other teams who looked at the data and have some questions about it. And so I'd say right now I'm less convinced than I was a year ago that this might be real. I should say the original authors are still claiming the detection. And so this is a huge controversy right now in astronomy. Is this real or not? If it is real, it's very interesting. If it's not real, then it's of course less interesting. My guess is that it will end up not being true, and Venus is unlikely to be placed with life in the solar system. But if it is, this would be really fascinating, and we might have the answer in the next year or two. So with that, I'm going to end and just say, really, for the first time in human history, I think we're on the verge of answering perhaps the biggest question of all, which is, are we alone in the universe? And as I hope I've convinced you from our little calculation earlier, I think the odds of us being alone are very, very slim. And I think we'll actually have an answer probably within 10 or 20 years. And that's pretty exciting. So it's an exciting time to be an astronomer. It's an exciting time to be a human. And of course, there's all sorts of questions that come about if you find life elsewhere in the universe. It has huge implications for many other things. I'm not going to comment on that, but it will be quite interesting. So with that, I'm going to stop my screen share, and I'm happy to take questions if there are any. Thank you.
Sure.
I've got one question, actually, Doctor, and that is, within our solar system, I've read that the Earth is such, the only place Earth could have life is the distance from Earth to the sun, that if we're off like 1/100th of a degree closer or further away, I mean, really something like that, that life couldn't exist. So only Earth is situated to have life. Is that true?
No, I don't think it's true. I think it's maybe life as we have it here on Earth. So this is another thing I was going to emphasize, which I didn't. So I'm glad you asked this question, Tom, because often when I'm talking about life in the universe, I'm not necessarily talking about the evolved life that we have here on Earth, right? I'm not talking about creatures that are on Zoom, holding meetings. That's a very sophisticated thing that has taken us 4 billion years on Earth. Life started on Earth over 4 billion years ago. It's taken 4 billion years to get to the point where we could have this meeting today. That takes a lot of lucky circumstances to work out. And that definitely does rely on the temperature being just right, the composition of the Earth being just right. But astronomers often refer to what's called the habitable zone, which is the zone where we think you want to be for you to have life. And that zone is actually pretty wide in the solar system. It starts at about Venus and it goes about to Mars. And that is the zone where you could have liquid water on the surface of a planet. And so in fact, if Venus didn't have a thick atmosphere, as thick an atmosphere, you probably could have water on the surface of Venus. And we know there's liquid water on Mars. So I think that that's a bit of an exaggeration. But it is probably true that to get the very advanced life we have here that's evolved so perfectly, you probably do need a temperature and an atmosphere very similar to that on Earth. Does that make sense?
Okay, Ed, do you have a question?
Ed?
You're on mute.
What is the definition of life?
Well, that's a really good question, right? And there are lots of people who talk about this, but life is, there are several, it's something that has to propagate itself. It has to be able to reproduce on its own. It has to take in energy and release energy. So there are a bunch of properties for life. But once again, there are when I talk about life on Earth 4 billion years ago, I'm talking about really very simple, starting with single cell or multiple cell creatures, very, very simple things. I'm not really talking about life necessarily like us, which is very advanced. Does that make sense?
Another question? Steve.
I'm gonna put it in go.
Yes, first of all, thank you for putting me on your mailing list. It's a fascinating place to be, and so thank you very much. Can you talk about the implications of potentially having life on moons rather than on planets, in that the planet is revolving around the sun, but the moon is revolving around the particular planet, which is revolving around the sun?
Yeah, it's an interesting implication. And I would say that up until about 20 years ago, nobody ever considered that option, right? Everybody had been thinking about the planets. It was the discovery of these geysers on these moons that I think really led people to go, but wait, you could actually have them on the moon. And so you're right. If there was a life form on one of these moons, they would probably be orbiting a planet, which is almost certainly not going to have life. So Jupiter and Saturn don't have solid surfaces the way we think of them. You know, they are big, giant balls of hydrogen and helium. They would be pretty spectacular. If you were on one of these moons, you know, Jupiter would be very large on the sky and Saturn would be very large on the sky, much larger than the sun from where they're at. So it would be pretty spectacular, but it would be interesting. I guess I don't know. I hadn't really thought of it beyond that, except it would be a different perspective because you would have these other things in the sky that are dominating the gravity. I mean, the reason why the moon is around Jupiter is because Jupiter has a dominant gravitational force, right? And so it'd be weird. You're kind of living on the small part of this bigger system that's all going around the sun. Once again, I think it's unlikely that these are walking, talking, thinking creatures on any of these moons. They would be very, very simple, most likely, because the conditions really aren't great to have the evolution we've had here on Earth. But who knows? Yeah, it's an interesting thought. You're right. It would be an interesting. There probably is a sci-fi movie about it, or it seems like there should be. Somebody should be thinking about it. Nobody's asked me that question. That's a great question. Thanks.
Okay. I think Dwight has a question. Dwight?
Where's Dwight?
Let me unmute. Okay. Now you can hear me, correct?
Yes.
Correct.
Okay. Yeah. So I haven't really thought that much about the universe since the 50s when I started reading Asimov and the other SF writers.
Yeah.
But when I first heard you talk about geysers coming out of the Saturn or Jupiter moons and possible lakes on Titan, for a moment I was very excited. But these are not geysers of water. What elements would they be?
Well, we don't know. They could be. They likely are some combination of water and other things, but we actually don't know in detail what the composition of them is. But it likely is that they are water-like and so are water dominant. But we don't know for sure. And I think this is one of the things which has to be looked at.
Does that mean to say that it's warmer than 0 degrees centigrade?
Yeah, it is inside, and it is inside because the gravitational pull of Jupiter and Saturn are so strong that these moons are effectively, well, we know, right? On Earth, of course, the moon has a tidal effect on us. But Jupiter and Saturn have such strong gravity on these moons that they're basically, the cores of these planets are heated up to pretty warm temperatures. So yes, they are in fact, it could be very comparable to the temperatures here, surprisingly.
Wow.
Now, the outer part of the moon that is exposed to space is very, very cold. And that's why you have ice on the surface and then liquid underneath.
Huh.
That makes sense? Yeah, it's pretty cool.
Yeah. So it is exciting. Okay.
It is very exciting and very surprising. Once again, I'd say 20 years ago, nobody thought this was nothing we had on our radar as something that could happen.
Mm-hmm.
Okay, John, you have a question.
Before I ask my question, I wanted to introduce Erica Clark, who's at our meeting today. She is Professor Dr. Mulchaey's strategic coordinator, and she helped put this talk together for us today, I'm sure. My question is this: you described the next decade of being a very exciting time for astronomers, and are there a lot of people coming into that field, and do you have enough people getting into the field to get done what you really want to do? And lastly, part of the question is, how does one get compensated for being an astronomer?
That's the hardest question. But no, so the answer is there's a lot of people going into the field, far more than were when I came into the field 30 years ago.
Good.
And partly this is because you hear about astronomy all the time on the news. One of our supporters said to me the other day, it seems like there's a news story every day on astronomy. I'm like, well, yes, there is. And I think people are so intrigued by astronomy in the universe that we get a lot of attention from the press. It's not uncommon for a science story about the universe to be on the front page of the newspaper. And so because of that, there's a lot of young people interested in the field. That said, we don't need 1 billion astronomers on our planet. It's a wonderful thing to be able to do, but it is still a relatively small field. There's only about 10,000 professional astronomers in the whole world. And these are people who like get paid to do astronomy all the time, like myself. And most people who work in astronomy are university professors. And so they teach and they do other things. That's how they earn their income. Or they work for NASA, where they work on missions like Hubble or various things. I'm one of the very rare ones. So Carnegie is a really unique creature among all this, because Carnegie our organization was set up by Andrew Carnegie, and it is a pure research organization. We have an endowment that we live off of, and we pay people to get to do what they want as long as they're doing astronomy research. So it's like the best job of all astronomers, because we don't have to teach and we don't have to work on missions. But there are very few of us. That's a very, very rare thing in astronomy. So there are people who get paid, but it's usually attached to some other service or some other community. So for instance, UCLA has a very strong astronomy department. I've actually taught at UCLA. And, there are astronomers there, but they get paid because they teach.
Are there other questions? I don't see any hands.
Marcia
Okay,
has a question and a comment.
you're
Go
up.
ahead, Marcia.
Hi. Yeah, I didn't put it, well, except spell check messed it up in the chat. But are there any astronomers that are, investigating or, thinking about like the Martian Chronicles, going back to high school here? Because we're the only species that has to make the planet adjust to fit us,
Yeah,
and we're the only species that's destroying the planet.
that is all true.
Are they wondering about, are we the Martians, so to speak? Did we come from another planet?
So there's a lot of question about how life starts and where it came from, and whether life on Earth in general came from somewhere else. That is one possibility. What I'll say is that I think that we understand we have a pretty good track record of Earth of being able to trace life back in time. And it's pretty clear that there's been a lot of evolution to get to this environment destroying aliens that we are today, as you mentioned. And so I think it's unlikely that we came as humans from somewhere else. But there is, of course, some chance that life or some of the elements that started life came from a comet or an asteroid or something. We see a lot of the components that make up very basic life out in the universe. There's gas clouds that have amino acids and things, weird sorts of chemical things. So it's entirely possible that some of that has come from outside, but I think the track record here on Earth is pretty clear. There's been a long history of 4 billion years of evolution. But I am going to follow up on one thing you said about destroying the Earth. And I think that's an important thing, because there's absolutely no question among us scientists that we are damaging our Earth in a very significant way. So even though I gave you that huge number with all those zeros behind it, which is a great experiment to show how many planets there are, we still do not know of another planet like Earth. And what I mean by that is a planet that is the right distance from its star, that the temperature is right, that it has the right composition of an atmosphere, that it has a strong magnetic field, which keeps away things from falling, storms from the sun hitting us. All sorts of things make Earth very special. We have yet to really find a true twin of the Earth. And so we don't know how common planets like Earth are. And so although I think life is probably very common in the universe, I think evolved life like us might be pretty rare. That we don't know. And so, but the lesson here is that we don't have another place to go. So we should be paying attention to the planet that we have.
Mm-hmm. Thank you.
Sure. I see there's more questions have come up.
Mark, you're up.
Approximately,
I think
sorry.
Mark had a question.
approximately, who, Mark?
Mark, go ahead.
Okay.
Go back to.
Of all the thousands of TV shows and movies, Star Trek and Star Wars and Independence Day and everything else with Martian Chronicles and so forth, have any of them struck you as even having a remote minutia chance of accurately reflecting what reality of first contact with an alien species could possibly be like?
I'll tell you the best, in my opinion, and it's a movie I love, but some astronomers hate, but many of us love it, is Contact. You'll remember the movie from the late 90s that starred Jodie Foster. And the reason why that's so good is because that book was written by Carl Sagan, who of course was an astronomer. And so the astronomy piece of it is actually really well established. So for those of you who've seen, if you haven't seen the movie, I think it's worth seeing. Where, you know, the fact that she's listening for the aliens using the radio telescopes at the VLA, the Very Large Array in New Mexico, that's a real place. They filmed it at the Very Large Array. I mean, I've been there and used that telescope. So I think that portion of it's really good. Now, they added the love interest in the movie that is not in the book. Because so that part is a little Hollywood and hokey. But the actual, in terms of the communication with the aliens, that, you know, where they build the structure and who knows? I think the reality is the universe is so big and immense that I think I told you, regular radio and TV waves and stuff are not going to work to communicate. That doesn't mean that there's not a civilization out there that knows some very advanced way of communicating, like they talk about in Contact. It's just so beyond anything we know that I think it would be very hard for us to even recognize it. So, but I love that movie because I think the science portion is actually really quite accurate. They did a good job.
Okay, thank you.
So
Sure.
my question is, by the time we see the light from the stars that we see every night, how many millions or thousands of years has that light traveled, just on average? 100 million years, 50 million years?
Yeah, that's a great question. And the answer is most of the stars you see with your naked eye. So if you go out from a dark place in the desert or something in California, the vast majority of all those stars are in our own Milky Way galaxy, and most of them are pretty nearby. So in most cases, they're hundreds or thousands of light years away. So you're talking within a few thousand years. We, as astronomers, can see things billions of years away, but they're very faint. You need telescopes for those. And so most of the stars you see are actually pretty nearby. They're, as I said, hundreds or thousands of light years away.
And then my last question is, what's the difference, just the basic difference between a star and a planet?
So a star is something that creates energy through nuclear fusion. So in the case of the sun, it's converting hydrogen to helium and producing energy. And a planet doesn't. And so there is an interesting category in between. There's these things called brown dwarfs, which are almost stars, but not quite. They don't really produce the nuclear fusion. So there's kind of a transition category. But for the most part, planets are things that don't produce their own energy.
Okay, thank you.
Any other questions? Ed, you have another one. You're on mute, Ed.
Nadeem has a question too.
Okay, the sun is slowly burning itself out. So how long does the sun have before it becomes a dwarf or enlarged or whatever?
Yeah, it has about 5 billion years. So this is one of the things you don't have to worry about. It's about halfway through its life. So the sun will kind of have a very constant energy level for about 10 billion years total, but it's about almost 5 billion years into that. So we have another 5 billion years. That is an interesting factor because there are some stars that only live millions of years. These are the biggest stars. And then there's other stars that live much longer. But what this means is, since I keep saying evolution on Earth has happened for 4 billion years. If we were around a star that only lived millions of years, we would not be here because we would not have had time to evolve. And so, although I've given you this, once again, this very giant number, the reality is there's certain types of stars. Not every star is probably a good place for life. And so, but the sun, as we know, is a good one. But we have 5 billion years. So that is something not to worry about tonight.
Thank God.
Something.
All right, I think Steve has another question.
Yeah, just a quick question. As an astronomer, do you look at the Earth and the heat at the center of the Earth radiating out, and how long is that going to go on?
So I think you're just talking about the heat, internal heat from at the center of the core of the Earth, you mean?
That's right.
Yeah.
That's
So
right.
I do not study that. However, we have Carnegie scientists who do. They really are geophysicists, geochemists. And it turns out to be really quite interesting because that heat is important for a lot of reasons. One, it of course led to volcanoes, which led to an atmosphere and an ocean. It also leads to plate tectonics, which is moving us around, which has been important for humans. And so, in fact, a very interesting area of study that many of our scientists, many of our Carnegie scientists who are not astronomers are working on is, do we need those factors to have life? How important is the fact that we have plate tectonics? It turns out it's important. How important is it that we have the moon? Because the moon allows tidal forces, which means lakes don't freeze necessarily because of tides, which is good for, there's a lot of different factors that probably make Earth really the ideal place for life. And so there are geophysicists and geochemists, those are the folks doing that kind of study. It's a really interesting question. In terms of when that will run out, it doesn't run out for billions of years. So it's a very slow process. So that's another thing not to worry about tonight.
Well, John, I tell you that you are one of the most interesting and intriguing speakers we have. Thank you so much for coming, and thank you, Erica, for setting this up. But wonderful presentation, and I'm sure we're going to be asking you to come back at some point for another subject. So, but appreciation of that. We are making a donation to the Westwood Village Rotary Library in your honor, making a contribution. Did somebody say something?
I was just going to say, Vadim, our guest, kept having his hand up for a question.
Who was that?
Oh,
Our guest, Vadim. If I may be
I mean, if we run out of time, that's fine. Yeah, my question was that apparently we're searching for life as we know it, right? So something
that's
like,
right.
You know, biological life, carbon based, and so on and so forth. So you know, but what is your opinion? What is the I guess likelihood that we can find other forms of life, like silicon based or plasma based, or
right? So my biology friends that's a great question. By the way, I put my email in the chat. If anybody has a question you couldn't get to, you feel free to drop me an email. Or if you'd like to sign up to Carnegie's email distribution, you can drop me a note. So I just put that in there in case so there were some other questions. The answer is, I think we don't really know. My biology friends tell me that there's reasons why carbon is very special, and they insist that it will be carbon-based. I'm not so convinced. The universe always has a surprise for you. And so I think we could be seeing life in some ways and not even know it because we don't recognize it. So I think your question's a really great one. And people are starting to look at alternatives, but it's really hard when you don't have examples on Earth.
Right. Thank you.
Thank you once again, John. With that, I think we'll conclude today's meeting. And thank you so much. Again, we are making a contribution to the Westwood Village Library in your honor. So
that's really wonderful. Thank you, everybody. Thanks for the great questions.
Thank you. Great presentation.